All right, good morning, everybody, and welcome to the Illinois EPA Public Water Infrastructure Energy Efficiency Program webinar today, Aeration Control Strategies for Lagoon Systems, it should say. We'll change that title slide there. But thank you for joining us this morning. We have some wonderful speakers today joining us, and I'm so excited for them to speak. We have Ben Shackman from Triple Point. We have David Shaffer, who's the Director of Public Works and Village Engineer for the Village of Hayworth. And we also have Sean Maurer, our Senior Energy Engineer today. We will record this session today, so a recording will be provided once it's available after we conclude the event. If you have any questions throughout the session, please either pop them in the chat or pop them in the Q&A box, and we will have time for some questions and answer at the end of the session. Also, it's wonderful. I love everybody saying hi in the chat. Say hello, say where you're from. It's great to have everybody in the room and have this community of wastewater plants that are interested in energy reductions. So also CEUs, you don't have to email me anymore for CEUs. I will send out the course number and certificates. We did get word from the Bureau of Water that our certificates and course numbers will be approved later this week. So that will be sent out to you as soon as possible. I see in the chat for the last webinar that we had on January 11th, those will come towards the end of the week as well. So hang tight, never fear, certificates and course numbers are coming, and we've never had a problem getting them approved. They just are backed up, which is understandable. They have a lot going on over at the training office. So they're coming soon, and I will get them to you as soon as I can. All right. So I'm excited to talk a little bit first about our energy assessment program. Then I'll turn it over to Sean to give us some basics, Ben to dig in a little bit further, and David to close us out with some of the stuff that he's doing at the Village of Hayworth. So before we get started, again, CDAC, we're the Smart Energy Design Assistance Center, and we're a partner with the Illinois EPA Office of Energy. And really our goal is to help reduce the footprint of Illinois and beyond. And through our partnership with the Office of Energy, we help run in partnership with the Illinois Sustainable Technology Center, the Public Water Infrastructure Energy Assessment Program. So we really just want to help you reduce the cost of water and wastewater treatment. So through this program, we provide educational events just like this. We provide free energy assessments and technical assistance. So whether you are investigating energy savings at your plant or don't know what to do and want to get started, there's some great technical assistance available through this program to help you navigate ways to reduce energy use and costs. We also have our comprehensive reports that come out of our energy assessments, and we really do a lot of digging into, cost of upgrades for recommendations, payback period, and we also look at applicable incentives or funding opportunities, which is really exciting. So if you're interested, I will pop that link in the chat in a little bit, but we want to talk about why you should think about completing an energy assessment if you haven't yet already. So if you have an older system or you haven't had a previous assessment, it's always a great opportunity to see what's out there, what could be improved at your plant, and how you could be more energy efficient. You can plan for capital improvements and then gain that third-party support for your ideas. I know a lot of our operators that get energy assessments really use our reports as a roadmap and a plan to present to council members or supervisory staff to get work done at your wastewater treatment plant. So it's a great opportunity to dig in, see what's possible, see what dollars are available, and also see how you can reduce your energy use. If you're a newer plant or you've recently upgraded your plant, it's always good to check in and see if there are any ways to improve or make sure that your systems are functioning well. So you can plan for those future opportunities outside of your recent project scope, or even explore some new technologies that are available. So either way, we highly recommend that. It's a great thing to do an energy assessment, check in on where you're at, benchmark your energy use, and see if there are any ideas or opportunities for upgrades or improvement. And of course, the funding is also a really great opportunity as well. So energy assessments, really, there's a kind of a pre-qualification that we go through. You have to be a plant located publicly owned and in Illinois. You have to allow us to come visit your site, which is always, I think, the fun part. You are also asked to be willing to share facility information like utility data, process flow diagrams, just so we can get to know your plants a little bit more. And then be willing to share the final assessment report with the Illinois EPA Office of Energy. So not regulatory, just with our Office of Energy to see what energy savings you have. So data collection is the next step once you meet those qualifications. So we ask for your discharge reports, process flow diagrams, utility bills. We pull the DMRs for you, but really that's the meat of your work as an operator, helping us collect that data so we can do our assessment and then walking through your plant with us. Once that's complete, then we provide that comprehensive report with all of those energy saving opportunities and ideas and all of those potential funding opportunities for that work. So we'd love for you to apply for an energy assessment. If you're interested, again, I'll pop the link in the chat. It's never too late to get started. And always keep us in mind if you have any projects that you're looking into. We also provide project assistance and technical assistance. So if you're just interested in lighting or VFDs, we can do some calcs for you to help identify energy savings and also funding. But energy assessments are a great opportunity to dig deeper. So let us know if you're interested in an energy assessment. All right, now I'm going to turn it over to my colleague, Sean Maurer. He's a senior energy engineer here at CDAC, and he's going to do an intro on aeration control. Thanks, Sean.
All right, thank you, Cassie. I'll go ahead, jump right in on the next slide here. Just a couple things we're going to talk about, some control basics. What we see at most lagoon facilities is some manual control of aeration systems. And usually it's because the funding that was initially available didn't allow for a full automation system or advanced control of aeration systems for a lagoon system. And it can be an effective means of control for smaller plants with tighter budgets, especially if you've got predictable loading. But for larger plants, or if you've got highly variable flows and nutrient loadings coming in the plant, you've got a lot of I&I maybe that could adjust the concentrations coming into your facility, then manual control is not really a great option for trying to maintain high quality effluent coming out of the plant. And so that's where automated controls can kick in. We see this a lot at larger plants, but it's difficult to implement well at lagoon systems, mainly because of the large surface area. So you've got a lot of different zones in the lagoon that can pop up. You've got well mixed zones, you've got kind of low mixed quiescent areas that are a little more calm. You've got varying levels of DO just from the depth of the lagoon. And so trying to monitor all that with an automation system takes a lot of sensing capacity and can really increase the cost of an automation system. And so we tend to see if there is automation at a lagoon system, it's kind of on a basic level, such as like timers or something that are automating the cycling or speed of blower systems based on known patterns of diurnal flows coming into the plant, diurnal loadings. But it's difficult to implement advanced controls at lagoon systems. So what we want to touch on today on our next slide here are ways that plants can control the different factors in their lagoons, ways to monitor what's going on so they can maintain high efficiency in their systems. So we'll touch on proper sampling procedures, optimizing mixing energy for the lagoon, and optimizing aeration energy. Part of that is separating those two where we can. Because if you're using your aeration to provide mixing, most of the time you're going to be over aerating your lagoon. And that just results in wasted energy. And then something else to look into is controlling algae and duckweed, using that to its advantage during the day when you're getting essentially free dissolved oxygen into your water, but mitigating the effect it has on your system at night when the algae starts to respirate and actually puts CO2 back into the water. It absorbs oxygen. And duckweed, where die-offs and things like that can also affect solids content and have a negative impact on your DO. On our next slide, the first step is to understand what type of lagoon do you have. At a facultative lagoon, there's normally no aeration. You're just admitting influent into the lagoon, letting solids settle out. You're pretty much doing an anaerobic digestion of that sludge at the base of the lagoon. A partial mix lagoon, is what CDAC runs across most frequently in our assessments for municipal lagoons. Aeration is for BOD removal and generally maintains some suspension of solids, but there is some settling into the lagoon that over a certain amount of time that sludge does need to be removed to maintain the lagoon depth and proper retention times for complete digestion. And then complete mixed lagoons will have enough aeration to maintain solids in suspension and prevent settling. Usually we see these more in industrial facilities, not so much at municipal plants, where they're trying to more rapidly and in a smaller area reduce the number of nutrients in that water. One thing to know about facultative lagoons is because there's a lack of mixing there, they're also poorer at reducing nitrogen and phosphorus nutrients. So we are seeing as permit limits for nitrogen and phosphorus are coming down the line that some facultative lagoons are upgrading their to a partial mix type system to better remove those nutrients and to also increase their treatment capacity. And for complete mixed lagoons, the main difference between them and partial mix, again, is maintaining those solids in suspension. So there's 25% or more additional aeration energy added in to those types of systems to maintain that mixing energy. But on the other hand, their processing time is generally reduced because they have increased contact time between the microbes, the oxygen, and the nutrients that they're trying to remove from that system. And so the size of the system can be reduced slightly and the treatment time is reduced significantly. So on our next slide, touch on sampling and verification. It's very important in your lagoon systems to know what your DO levels are. Sampling ensures that you're getting that design oxygen transfer, that you're fully digesting the influent that's coming into the plant, and you're maintaining that high quality effluent. But knowing where to sample and when to sample are two very important things for controlling a lagoon. So as far as where to sample, you want to pick a well-mixed portion of the lagoon. You want to avoid quiescent areas because in a well-mixed portion, you're going to be getting the full content of solids that are in that lagoon. So you have a better idea of what's being digested. If you test in a quiescent area, there may not be as much DO being absorbed there. Your mixing may not actually be providing DO to that area. And so those values aren't going to be as representative of what's actually happening in your treatment system. Usually somewhere around your effluent chamber or effluent pipe is a good area to get that kind of sampling because you're picking up what's transferring out of your lagoon to the next cell of the lagoon or into your effluent. As far as when to sample, early in the morning or at the end of the day when the impact of algae on your lagoon is not as large as it is in the middle of the day. When the sun is shining into that lagoon, you're getting a lot more DO for free from algae. And if you've got plants like duckweed growing in the lagoon system, those are going to increase your DO readings from what's typical. And so those early morning periods or end of the day periods when the sun isn't adding as much energy to that system are better times to take that information. And while those are good recommendations as far as for reporting purposes when to take those samples, it's also good to take samples at multiple times during the day, multiple depths and multiple locations so that you understand what your entire lagoon is doing. And I think Ben and David can both talk a little bit about that in their presentations. On our next slide, a critical concern for partial mixed lagoons is making sure that you're preventing short circuiting and getting effective mixing in the system. As we look through the literature, doing a little bit of research on this, we found a couple of examples that we just wanted to put kind of a graphical representation of here. On the left side of this screen was a lagoon that had two or a few aerators kind of centrally located in the lagoon. But they had an effluent pipe on one side and an influent pipe kind of in the center on the opposite end of the lagoon. And what was happening was with those aerators right in the center, they were having a short circuit around that aeration system along the shortest path to the lagoon to the effluent pipe. So they weren't getting full use out of the entire lagoon system. And the fix was just simply shifting those aerators and mixers a few feet to the side to increase mixing in that area and force the path of flow to use the entire lagoon. That increased the retention time for solids and influent into that lagoon area and increase the effectiveness of that operation. And similarly for lagoons with multiple aerators and stages, typically we see they're set out in a grid pattern. And what can happen with this grid pattern is sludge can build up in mounds and create a short circuit path, and flow can go straight through those. So if you can stagger your aeration a little bit, it helps ensure that any direct flow paths are broken up. And again, you're getting full use of the entire lagoon cell for treatment capacity. A couple of ways you can check for short circuiting that we've seen, ping pong balls or any kind of floating material you can input into your influent pipe, see where that path goes through your lagoon and time it, see how long it takes to get through that lagoon process. It's a good way to check for any kind of short circuiting paths. Do a couple of tests, see what kind of pathways are flowing through your lagoon cells. What we're talking about here are the different types of aeration systems and how they impact mixing in the system. One of the things we like to promote is looking for ways to do some kind of horizontal mixing or overlapping vertical mixing's area of effect so that you minimize the risk of having settling between your aerators that can create those flow channels that'll exacerbate short circuiting. So on the top right corner there, you can see there's a couple of aerators, and where there's some updraft of flow because of either the way they're mixing or splashing, or if it's a subsurface diffuser where you've got the airlift happening from the aeration system. There's enough mixing there that sludge doesn't really settle, so that's a low spot in your sludge. But between them is where you can have settling happen. And we can see this a lot with lagoons now that are doing tapered aeration, where you've got a lot of mixing at the head of the lagoon cell, but you have fewer mixers towards the end because you don't need as much DO in the process. You do have a little bit more risk then of having settling between the aerators. So it's important to look at, as well as the aeration effectiveness, what's the mixing effectiveness of your aeration system? And so a couple of things to look at here. For shallow lagoons, we're looking at 8 to 10 foot depth that we usually see for converted facultative lagoons or something like that. Surface aeration mixers can provide adequate mixing all the way to depth in a horizontal pattern that can help break up any kind of sludge mounding at the bottom of the lagoon and prevent short circuiting paths. If you do find paths, they're easy to adjust the direction that you're forcing flow out of those aerators to change the way that flow happens in your lagoon. There are also options. Center picture on the bottom there is a hyperboloid mixer. Essentially draws water from a horizontal path and creates an outward horizontal flow off of that mixer that can divest your mixing from your aeration. So you've got kind of a reduced horsepower requirement when you're just doing mixing only. And then the last picture on the right bottom there is vertical mixers from aerators. Again, if you're looking at subsurface diffused aeration, you want to look at what's the area of effect of mixing that those are going to generate and make sure that there's a little bit of overlap between them so that you don't have mounding between your aerators. This is just a comparison of mixing energies for those different types of mixers. So you can see submersible mixers is kind of like that surface turbine mixer where you're generating a jet of bubbles under the water. There are also propeller type mixers that we see for activated sludge plants that some lagoons might use. But generally these are these surface mounted floating aerators that have a little propeller at the end, and they're inducing some aeration flow through the shaft of that aerator. Those are on the higher end for energy mixing. They can be at the lower end. You can see there kind of the middle of the chart. One thing to be aware of is the large bubble column there isn't coarse bubble diffusers. It's talking about a compressed air system that has a special diffuser that creates a large bubble that's on the order of a few inches in diameter. It creates a large uplift without a lot of oxygen transfer. So you get mixing without DO, which can provide some energy savings there. So just an idea of the different types of mixing systems that are out there and available and how to minimize energy for mixing. On our next slide, we're looking at minimizing the energy use for aeration. So the different types of aerators, and what we're showing here on the chart is pounds of O2 per pound of horsepower, or per horsepower hour of energy consumption. One thing to be aware of when looking at these diffuser systems and comparing them to each other is being aware of the alpha factor of your lagoon influent, because that has a large impact on how efficient these systems are. For surface aeration systems, because you're splashing water into the air to get mixing, usually those are less impacted by alpha factor, but they're lower efficiency to begin with. For submerged systems that are injecting bubbles from the surface into the water, again, they're a little less impacted by the alpha factor because the bubbles aren't retained as long. If you've got surfactants in the water, they can't bind to the surface of that bubble and reduce transfer through that air to water membrane. But the big difference to be tracking that alpha factor is between coarse bubble and fine bubble systems. Again, coarse bubble, because those bubbles are larger, they're generating more turbulence in the water, a little bit better mixing than you get with fine bubble. While they're less efficient at transferring oxygen just because of the reduced surface area, they are a little bit better at maintaining their oxygen transfer efficiency, being less impacted by the alpha factor. Where fine bubble, because those bubbles are much smaller, they rise slower through the water, surfactants can bind to them and reduce the transfer of oxygen through that membrane. So when you're comparing these systems, make sure when you're talking to any kind of distributor or contractor that they're taking into account the alpha factor on that system and not giving you the clean water efficiencies only of these systems, or they can be a little bit misleading. Something else to be aware of when looking at these, when you're looking at pounds per horsepower hour listed there, keep in mind that it's not pounds of air delivered, it's pounds of oxygen delivered. And oxygen is only about 20% of the air content. So if you're looking at your own plant, kind of comparing where you're at on this list, and you're calculating pounds of air delivered per horsepower hour, only 20% of that is actually oxygen, 23%. So make sure to do that math that you're accounting properly. It's pounds of oxygen per horsepower hour that you're comparing here. On our next slide, we're looking at calculating the lagoon oxygen transfer. What are your needs, and what factors are impacting that oxygen transfer rate? So first is needing to know what's the design for that oxygen demand. If you're looking at the 10 state standards, which a lot of Illinois designs follow, they recommend 1.1 pounds of O2 per pound for the peak daily BOD5 demand coming into the plant, unless you've got an experimentally determined value. And we do see 1.5 to 2 pounds of O2 per pound of BOD as well. Usually that applies more to extended aeration plants, where they're also doing denitrification and other nutrient removal processes. So that 1.1 is kind of a generalized standard for short solids retention time periods. If you're doing extended solids retention, then you may be looking at more like a 1.5 pounds per pound of BOD. But what can affect that oxygen transfer rate? Something to be aware of is the water temperature itself. The colder the temperature of the water, the easier it is to dissolve oxygen into it, which will reduce your demand, and the less microbial activity you have, which also reduces your aeration demand. And so being aware of seasonal adjustments and how much aeration you need to provide is important to be aware of. Algae and duckweed, during the day, those are going to be providing DO, and at night, they're going to consume it. So you're going to need more aeration at night. During the day, we've seen plants that don't need to aerate at all. They get enough DO. They just need to do a little bit of mixing to make sure it gets through the full water column. And as I mentioned before, being aware of the alpha factor is very important to make sure that the system you have installed is going to adequately provide the oxygen you need. On our next slide, talking again about minimizing your aeration energy. Target DO levels for lagoons are somewhere around 2 milligrams per liter at a maximum. We regularly see 4 to 6 milligrams per liter happening, and a lot of times it's because they're trying to maintain that mixing with an aeration system. What we have seen a lot of plants do is pulsed aeration, or cycling their aeration on and off. to maintain an average DO around 2 milligrams per liter. That's been very effective. For deeper lagoons, using fine bubble systems is a good way to minimize that aeration energy requirement. Tapering your aeration, where you've got a lot of aeration at your influent, where your BOD demand is highest, and fewer aerators towards the end of the cell, where you've actually consumed a lot of that BOD and you don't have as much activity anymore. And then optimally, you want to try to divest your aeration from your mixing. We don't see it a lot with lagoon systems. Usually the aeration is also providing the mixing. But if you look at maybe mixing types of aeration systems, using a coarse bubble with reduced DO to provide mixing, and then fine bubble to provide DO when you need it. On our next slide here, we'll zip through these kind of quick. Duckweed and algae control, some issues that duckweed and algae can cause. If you get a thick mat of it, can block sunlight, which will reduce DO levels from algae deeper in the water column. Can increase fecal coliform levels because you're not getting as much treatment out of the entire depth of your lagoon. They die off in the winter months, and at night they consume your DO, which can increase your aeration needs, which is that diurnal cycle. And so while you can take advantage of these, they do need to be somewhat controlled in your system. And on our last slide here, we'll touch on ways to control. For duckweed, you can rake it off manually to try to control it. You can raise plant-eating fish, such as grass carp in your lagoons. They can consume those plant materials, keep them at a minimum. Or if you've got a severe problem, aquatic herbicides are available that can control that. For algae control, mixing is a good way to control algae, especially at night. As they're respirating, they are dissolving CO2 into the water column, and then the next day they draw that CO2 again, and that can create large blooms of algae. And so if you're doing mixing at night, it can release that CO2 into the air and then reduce how much growth you have the next day. Barley straw is a natural way to control as well. As it decays, research has shown that it releases hydrogen peroxide into the water, which can control the growth of algae. If you float some bales on the surface, that natural decomposition is a good way that we've seen. If you get it into the lagoon before the algae starts to grow, it's a good way to control it. If the algae is already there, it's not going to do much for you. So it's good to get that in ahead of time. Sludge reduction. If your lagoon has a high sludge column in it, you're not having as much treatment capacity, that can also impact algae growth. If you do need to use chemicals, using chelated copper is recommended. Unlike copper sulfate or other additives, it stays in suspension longer, so it reduces how much you need to use, and it reduces how much sludge is created from adding chemicals. So now I'll turn it over to Ben. He can go into a little bit more detail on those control strategies.
Thank you so much, Sean, for being willing to present. That was an awesome introduction. And thank you, Ben, for joining us today. Ben Scheckman has been involved in the water and facilities business for the last 9 years and holds an MBA from the University of Illinois. Go Illini. His background includes high purity, utility, and wastewater experience, both at NALCO and Evoqua. So before entering the water business, he spent over 26 years in the U.S. Army. Ben's been certified as an instructor both by the U.S. Army School at Fort Knox and the Officer Candidate School at Fort Benning. Additionally, he's taught as an adjunct professor at the graduate level. So thanks for joining us, Ben. So excited to have you speak today.
Cassie, it's my pleasure. Can I just ask you to confirm that you see the slides and you hear my voice?
Yes, I hear you and it looks great.
Okay, thank you so much. We are off to the races, folks. Let's dive right in. So looking on the left side of the screen, our source here is the US EPA. And if you take a look at the biggest chunk of that graph, where's that coming from? Where is the energy consumption in our wastewater treatment plants coming from? Aeration, absolutely aeration. Bottom left of the screen, NREL, they're showing a higher percentage of the energy consumed running a plant coming from aeration. Top right, University of Minnesota, again, something north of 50% of the energy coming from aeration. And I love this one on the bottom right here. This is a comparison out of South Africa. And what we're looking at is different types of treatment technologies, the electricity intensity. So how much energy, how many kilowatt hours does it take to treat, in this example, a cubic meter of wastewater? Looking at energy and looking at greenhouse gas emissions. And guess what? Lagoons do it better, plain and simple. Lagoons consume less energy, lead to less greenhouse gas emissions. And when you look at the small communities scattered around the United States, about 8,000 lagoons out in the wild right now. Going back to a comment Sean made about facultative systems, out of those 8,000 or so systems in the United States, about 60% of those systems right now, 60% are facultative. There's no mechanical aeration in those systems. They're just big holes in the ground that they dump some relatively nasty stuff into, and they get a whole lot less nasty stuff out the back end of it 60, 90, 120 days later through the miracle of science and microbiology. So next up, I've got a quick quiz, and I'm just going to ask, which do you think requires less energy? Is it blowing air into water, or is it throwing the water up into the air? I see Cassie's popped that up for us on the screen. We'll give it a couple of seconds, and then we'll jump to the next slide here. All right, Cassie, hopefully everyone's had an opportunity to enter their answers, and there's some feedback. Yes. So yeah, that's right. Blowing air into water is going to consume less energy. It is unequivocally correct that it is easier, it costs less to move air than it does water. It's just a less dense substance, so it's less energy intensive to move around. And from our perspective, fine bubble aeration, absolutely the way to economize on the cost of getting air into water. So looking at bubble size and thinking about efficiency, over on the left there, we've got fine, medium, and coarse bubble, 3 different sizes. In the center column, we're looking at SOT, standard oxygen transfer equivalence. SOT does not take the alpha into account, but SOT is how you establish a level playing field to compare everyone's products that are on the market. I will tell you that looking at fine bubble, you should be seeing very, very small bubbles up to about 3 millimeters in diameter. Medium and coarse get larger from there. And if we want to think about this a little bit differently, we can think about the volume of air that goes into a cubic foot. So a 1 cubic foot bubble, that would be a really big bubble, and it would have 4.8 square feet of surface area. Surface area is important because it's that liquid air interface where oxygen transfer occurs, where you move oxygen out of the bubble and into the water. So 4.8 square feet, a cubic foot of air, it's going to rise incredibly fast to the surface, and it's going to transfer very little oxygen as a result. We can step down and look at what it looks like if we break it up into 4 bubbles. Now we're up to 185 square feet. And if we break it down further, you can see the math here is progressing. The smaller the bubble, the greater the surface area. The greater the surface area, the greater the efficiency with which you can transfer oxygen to water. We can see that on the graph here. On that vertical axis, we have pounds of oxygen per horsepower hour. Reiterating Sean's comment, about 21% of the air that we breathe at sea level, standard atmosphere, about 21% of that air is oxygen, approximately 78% nitrogen mixed in there. The nitrogen does nothing as far as inspiring and facilitating microbial activity. It's really all about the oxygen. And if for that same horsepower hour, you can transfer more oxygen to the water, if we're looking at a system where dissolved oxygen is what you need, it's unequivocally better to transfer more oxygen per horsepower hour. That is how you spend less money to properly oxygenate your ponds. This model shows about a 10-foot depth, and fine bubble aeration is the top line, and you do see a slight degradation as you increase the airflow. The hotter you run a membrane system, the less efficient it becomes. So if you're pushing out at 50 or 100 SCFM, you're going to see a reduction, and it may make more sense. It may make sense to go back to the consulting engineer and say, hey, model a little bit lower flux rate. Let's see what that looks like. Find that sweet spot in the design where you'll get all of the dissolved oxygen, all of the mixing at the lowest possible airflow, lowest energy consumption as a result. And this is an example of third-party independent verification. This is on products we manufacture. I will just say that if you are not getting third-party independent verification from an aerator manufacturer, if they can't provide full-scale testing of a production unit, probably you want to talk to a different manufacturer because the transparency is just not there. And then when you start complicating the conversation by adding the alpha, the beta, and the theta to the conversation, Sean discussed the alpha bit. Beta and theta take a bit longer than we really have time for today. But when you start to further complicate the conversation by degrading or derating from SOAT, it's so important that you're starting from third-party independent verification so that any deration that takes place as you take alpha, beta, and theta into account, you're starting from a good number, so you're going to arrive at a more accurate number as a result. We talked a bit, we heard Sean talk a bit about aeration and what it does for us, and mixing. Mixing is so important also. And the level of mixing, that's really and truly about how well those metabolizing microorganisms come into contact with the food source, the biochemical oxygen demand, the nutrients in the pond. And the level of mixing is that it's going to determine how much can be treated and how quickly you can treat it. In fact, one of the levers that we pull when we're doing designs for undersized, overstressed systems is we look at adding additional aeration and mixing very specifically in order to increase that treatment rate, to get more complete treatment out of existing infrastructure. It's just one of the levers that we can pull. I've got a note on here also about not letting your aerators get ragged up. It's so important to maintain the efficiency of what you've got in your system. And if you don't have screening on the front end, please think about that. And we're not a company that does anything with screening. It's just an industry best practice recommendation. If you can keep all the plastic, the applicators, and especially those flushable wipes, if you can keep that stuff out of your pond, you run less of a risk of ragging up an aerator, reducing the efficiency of an aerator, or even potentially seeing, and this is not specific to diffused aeration, ragging affects all types of aeration and it robs efficiency. So please keep the aerators nice and clean, keep them working as best you possibly can. It's only going to benefit you and your system. So looking at pounds of oxygen required to do the work that we need to do in our systems. Sean had a number of 1.1. That's a valid number. 1.2 is a valid number. 1.5, 1.7. Every state, it seems, likes a little bit different number, and they drive their designs in that direction. So it's important that your consulting engineer is licensed in your state so that they know what the state EPA or the DNR, whoever writes your NPDES and approves systems for construction, your permitting agency. So important to understand what number they like and design around that. So much easier than arguing with a regulating body about, no, it shouldn't be 1.5, it should be 1.3 or 1.1. Easier to go with their numbers, and that ensures that your system gets permitted and moves on to funding much faster. But I want to pause on this slide and I want to talk for just a second about the different bugs, because BOD removers, those are heterotrophic bacteria. They can live and survive and float freely in the water column, and they're happy to do so. They're bigger, they're faster, they outcompete the autotrophs. The autotrophs are the little guys that remove ammonia for us, conducting those first couple of steps of the nitrification process. But they do it with a lot more air. So where we need to provide 1.1 up to maybe 2 pounds per pound to support BOD removal, our autotrophic friends, the Nitrosomonas, Nitrospira, Nitrobacter, those are the dominant species that do the work of nitrification. They need a lot more air, folks. They need 4.6 or so pounds per pound. And where there's a great deal of discussion around whether 1.3, 1.82, that's whether that's the right number. The range being discussed is much wider. It is rare to hear anyone talking about less than 4.5 or more than about 4.8 pounds of oxygen being required to support the autotrophic bacteria's life cycle and the work that they do for us. And that leads to differing levels of DO, and with that, the oxygen required. So just a reminder here, composition of air at sea level, approximately 21% oxygen. And we know, talking about efficient nutrient removal, efficient nitrification, the oxygen requirements, we know that the biological community consumes large amounts of oxygen. And if we take a look over at that chart on the bottom right, that is just this fantastic comparison that shows the cost, the direct expense associated with running varying levels of DO in the same system. What a great model to have. I mean, you can very, very easily see that at about 2 milligrams per liter of dissolved oxygen, $5,000 or so is the incremental cost. If you go up to 6, that's doubling. You're all the way up to $10,000 to run the same system. We talked about the amount of oxygen that's required. We talked about the residual as being what's left over after the bugs have consumed the last molecule that they need to support their life cycle and the work that they're doing for us. And I just really want to emphasize here that providing extra oxygen, that's just an extra expense. And when you control the conditions, you can control the results that you get. And a way to control conditions is by automating systems. So nitrox is our solution for ammonia. The technical description is a tertiary thermally regulated nitrifying moving bed biofilm reactor. And I could spend about an hour and explain all of that to you. But just know that us and the competing technologies on the market, we're growing the same bugs. We're just doing it on different types of media. There are folks out there that are growing them in the ponds. They're growing them on rocks. We're growing them on an extruded plastic product so that we're in a very small amount of space. But all of these types of systems benefit from automation. VFDs, if you can ramp that blower up and down in response to reading coming off of a DO sensor, and then you get really fancy and you add PID control in there. And we're going to talk about PID control next. So that's this slide. We're going to start on the top left here. We're going to start by looking at something out of Minnesota. This is an industrial, this is an OEM, Control Solutions in Minnesota. No endorsement express or implied. Lots of great control houses out there. I just really liked their diagram when I was out looking for a diagram to help me explain it. So I grabbed that one. So unpacking this diagram a little bit, we've got a set point and we've got a controller and then our process. And that process is subject to disturbances. In wastewater, that's a change in flow, a change in loading. As Sean pointed out, the diurnal nature of algae, you see rising and falling DO levels based on the organisms living in your systems. These are all disturbances, and the sensor is picking up the disturbance and it's providing data back to the PID controller based on that measured variable. And then that controller is making a bunch of decisions. We're going to jump over to the text now. So think about PID control as a control loop feedback mechanism. And we're changing a setting in response to a deviation from set point. And that's a whole lot to say and think about. So I'm going to make this a really simple example. It's getting on towards lunchtime here in the Midwest. And I'm guessing that most of the audience is contemplating getting up from wherever they're sitting and walking over to the refrigerator. Now, when you do that, your brain is telling your body to accelerate to your normal walking pace. Maybe you're really hungry and you're going to walk a little bit faster. Your brain's telling your body to do that. But as you approach that refrigerator, your brain is telling your body, hey, we're almost there, slow down. And you'll slow down, and probably 10 times out of 10, you'll stop before you run into that refrigerator. You'll be close enough that you can easily open the door and grab your snack. That is PID control. That is considering the difference between where you are and where you want to be, understanding and modeling the rate of change, and doing so in such a way that you land at set point. You don't overshoot it. So we're going to jump to the left now. And this example is from Pellet Grill Reviews. It's a website for people that are fond of barbecuing. And I fit into that category, folks. And I have a pellet grill. And there are pellet grills on the market that have PID control. And the graphic over on the left shows you how tightly they maintain their temperature. The graphic on the right, conventional control, you can see they're above and below set point. They're moving. They're trying to control to do 250 degrees. That sounds a lot like ribs to me. They're smoking ribs and they're bouncing up and down. They're above and below. And is that going to make a big difference in the flavor or the taste of the ribs? Ben's opinion is probably not. Will it consume more energy to create that same rack of ribs off of the smoker, though? Absolutely it will. Absolutely it will. And you compare that to tighter control on the left, where you're turning the heat on and off, where you're modulating it very, very slightly in order to stay tightly in control. We're going back to the right side of the screen now, proportional, integral, and derivative. The controller is going to look at all three. It's going to determine the rate of change needed to bring the process back into control. This is no different than your mind telling your body, hey, speed up. We got to get to the fridge before the wife gets there because she's going to steal the leftovers we plan to eat. And it monitors that rate of change and it adjusts to minimize overshooting, hunting, and porpoising. Overshooting, hunting, and porpoising, that's what you see on the right side of that graphic from the barbecue folks. But that's no different than monitoring DO or temperature or any of the variables that we would set up a PID controller on a wastewater treatment plant to monitor. I think it's important to point out that most industrial controllers out there running factories and such are PID controllers, and they are for a reason. It's about efficiency, and running any system within a tighter control is how you ensure that you're spending no more, no less on the energy that you need to run that system properly while getting the results that are required, not just desired, but required. Okay, so talking some more about monitoring DO and looking very specifically at some devices that you can do this with. It's important to remember that you're supporting the microbial communities in the pond. That's what DO is. That's what we're doing, is we're providing oxygen. We need to breathe, they need to breathe, not a lot different. What's left over, that's the residual. We've talked that a lot. And I think this horse has been beaten enough, but providing excess dissolved oxygen just results in excess expense. When and where you measure DO matters. Sean talked a little bit about this. I would suggest that you will see the full effect of algae's diurnal nature if you grab a sample before daybreak, same depth, same location, go back at solar noon when the sun is at its highest point. Photosynthesis is just rocking and rolling at that point. And that is where you'll see the greatest delta between your dissolved oxygen in your ponds. And it's important to understand the impact of algae and how it affects your treatment and oxygen in the water. And I can't emphasize this last bullet enough, folks. You've got to calibrate and maintain those sensors and meters. Otherwise, you don't know if you've got good data. And if you don't have good data, you can't make good decisions. You can't really tell what's going on in your system. If you're showing a 1 DO, but it's really 3 and you're ramping your blowers up, you're spending a big pile of money that you don't need to spend. And the culprit is a sensor that's not calibrated. Please calibrate and maintain those sensors to ensure accuracy in your readings. I've got a comparison for you. Looking at monitoring DO in lagoons and then in a tertiary ammonia removal is the example that I chose here. So in lagoons, in order to really understand DO, you have to measure it at multiple points. Our friends over in the statistics department would suggest that 30 is a statistically significant sample size. I'm not sure you need 30 measurements to adjust the DO in a wastewater lagoon, but we'll leave that to the statisticians to fight over. So measuring in multiple points. If you're automating this, you're going to need multiple sensors. And it's important to think seriously about the capacity to perform maintenance, the appetite to perform maintenance, and the budget for maintenance. More sensors means you're going to be spending more money to replace sensors as they reach the end of their life cycle and have to be replaced. You're also going to be performing more maintenance, and it could exceed the capacity of the staff. The highest demand, you're going to find that very typically near your influence structure. That's where BOD is highest, and that's where your aeration should be the highest. And Sean talked a bit about tapering aeration, and that's another way that you just increase the efficiency of a system. You're providing the air where it's needed in the right proportion to the loading. And long HRTs create differences. Long hydraulic retention times in these systems, they create differences in the DO. And it's entirely possible that if you're trying to measure your effluent DO and use that as your process variable and adjust your blowers, you're looking at DO in water that was treated. It could be 60 or 90 days after it was exposed to those aerators that you're now ramping up in response to low DO. Might not be the most efficient approach. Checking DO, again, talking about algae, and automating is a challenge, but for some systems, it could absolutely be the right answer. And I would recommend looking first and foremost at the staff and at the facility, and just having a frank conversation about what's realistic and what can be supported moving forward. Now, on the other side of the screen, in a tertiary process, and that's what we see very typically for ammonia removal, phosphorus removal is becoming a big thing also. Measuring residual at the end of the process makes a whole lot of sense. And in our systems, we're typically setting them up to run at about 3.5 hours of retention time within that process. So certainly it's a whole lot more realistic to control blowers based on 3 hours of HRT as opposed to trying to account for 90 days worth of HRT. And neat thing here, you only need one sensor because you've got such a small HRT, so it becomes easy to maintain and to automate this process. VFDs and PID control, we talked about that already. You're watching your DO automatically. You're automating this process. So in the middle of the night, if your DO crashes, you don't have to be there to see it. Your PID controller commands the blower to a new state, system recovers on its own. And it automates the data-driven decisions about blower speed. So rather than having to go out and take a bunch of readings and do all the math and then make a decision about what you want your blowers to be and figure out when you're going to reevaluate that, the system just does it for you. An example like that, automation just makes a ton of sense. Got another one here, a little quick quiz. And Cassie, would you like me to wait for that to pop up on the screen or just keep going?
Let's have everybody answer in the chat. If you want to just keep going, that'd be great.
Got it. So single biggest change you can make to your system to get it back to performing as it was designed to perform. Folks, put those handoff auto switches back in auto. If there's some reason why you can't, if a piece of the system doesn't work right, if a sensor's gone bad, if whatever it is, put the time, energy, and effort into figuring out how to get those handoff auto switches back in auto. Those switches, they are the biggest enemy of efficient operation. You had a lot of engineering, you spent a lot of money on the automation, and when you leave the switch in hand, you just block any potential savings associated with it. Then down at the bottom of the screen, very simply, you bought it, why not use it? Let's see, my slide here, this is a comparison, and I want to make the point that it's important to look beyond first cost when you're modeling out changes to your system and improvements. and ensure that you're looking at total life cycle cost. This example models 20 years. You could easily model 30 years. This is based on a half a million gallons a day ADF, 10 state standards for loading, and an 8 cents a kilowatt hour electric rate. Very typical for Illinois systems. And just a comparison between total cost of operating various different systems to accomplish the same end state. And Cassie, Sean, I hope I'm doing well on time because I'm at my conclusion slide. I just want to point out that working to improve the understanding of energy patterns and efficiency opportunities, it's a best practice that all communities can adopt. And if you're tracking your energy usage, you're benchmarking, you're making operational improvements, all communities can get going on reducing energy use and realize some financial savings. That's from the National Renewable Energy Laboratory, Golden, Colorado, one of their locations on the screen there. But I can't stress this strongly enough. I look at what's going on around the country. I look at energy programs around the country. CDAC is unique. The programs that are available in Illinois are unique, and they're the most lucrative in the nation. So I can't stress it enough to the audience. If you've got a lagoon system out there and you haven't had CDAC out to take a look at it, please give them a call. They can absolutely help you do it better.
Thank you so much, Ben, for your presentation and also your kind words about our assessment program. And also for our operators on the call, please put in your questions. I see some coming in, and we will answer them at the end. So thank you, Ben. Now moving over to David Shaffer. He is the Director of Public Works and Village Engineer at the Village of Hayworth. And you have a great aeration system over there. And I look forward to having you speak a little bit about the work you're doing in Hayworth. So thanks for joining us.
Thanks, Cassie. I don't know that I go so far as to say it's great. Ben, that was fantastic presentation. And there's a lot of things that you said that that ring true. And if people don't take much away from this, which they'd have to be asleep to not, I think the things that you said there about, you know, knowing your staff, knowing your ability to take on the additional maintenance and absorb that effort should drive a lot of your decisions, because it doesn't matter if you've got great automation. If you don't maintain it, then you're worse off than when you started. So Cassie asked me to share a few words about what we're doing, or what some of the things we've done in Hayworth are with our lagoons to try and save save some energy. And looking at your lagoons, you know, if you got a gravity flow lagoon system, there's not a lot of options for energy savings. You probably have a few lights around the lagoon. You should have already changed those to LEDs by now. You've got aeration, and then you maybe have some filter pumps, or maybe not. Yeah, and the one thing that a lot of people I think get lost on is, you know, your lagoon and that aeration equipment and your pumps were designed for that maximum capacity that was identified in your facility report. That might have been a 20 or a 40-year lifespan. You know, where are you at in that design? You know, if you're running a system that was designed for population of 4,000 people, you know, but you've only got 1,500 people feeding into it, why are you running everything at full capacity? You know, dial it back, try and find that efficient a point that gets you permit compliance without, you know, using more energy than you need to. You know, I'm an engineer. I spent a lot of time in consulting before I came over to work in the municipal side. And I'll be honest with you, a lot of engineers are blind to the fact that here's the regulations, here's where we're going to land to get you a permit, to get you your facility. And stepping back and saying, but how's it going to operate right now at 1/3 or 1/2 of where we expect to be in 20 or 40 years, gets lost a lot of times in the push to get something done, get a problem corrected. So sometimes it's good to step back and look at where are we at today, and then, you know, so what do we have that we can turn down, run at a lower speed or less often. So what are the things that you can control coming into your lagoons? Most people don't have a lot of control over the flows that come in. You're going to take what's given to you, whether that's, you know, your 100 gallons per day per person, or In my case, sometimes 300 or 400 gallons per day per person, depending on how much it rained the night before. So the only thing you really can control is your aeration and your pump speeds, your motor speeds, depending on what you're using. And then you've got your factors. Ben did a really good job talking about what factors you can control or you can use to control things off of. And what are those factors, whether it's dissolved oxygen, your flows, just using a timer. How do you integrate your energy saving controls in with what you currently have available? Are the things that you can do that are relatively easy, or you have to throw your entire control scheme out and start over? Because that's going to cost you a whole lot more money. And then long term, what are you looking at for O&M costs? You don't want to add something that adds a lot of additional O&M cost to your operation. You may, okay, great, we saved $10,000 a year on energy, but in order to maintain that, I've got to hire another guy that cost me $40,000 a year. That was a loss. That was terrible. So you need to look at a holistic approach. Take a step back, take a deep breath. Don't rush into it, but certainly figure out something that you can do. So for Hayworth, looking at my staff, looking at my available time, we said, we run a pretty simple system, and we don't have a lot of real technical staff. They're great with streets, they're great with fixing a water main break, but they're not real great on understanding process control and what actually happens in the lagoon. So we said, we've got a flow meter, takes our incoming flow. We're going to use that as kind of our data point for controlling our aeration. And then we're going to work from there. So we worked with our integrator saying, here's what we want to do. We know we're over aerating, but we don't want to lose our mixing. Here's the equipment we have. What can we do to control it? And it was a collaborative process to come up with a solution that said how we can control our aeration equipment. So we ended up spending about $21,000 on aeration controls, and looking at what we expected to save. We were thinking the ROI was going to be somewhere around 2 years. And we ended up with an energy rebate from Ameren for about $6,000 out of it as well, which drove it down even more. So what we did was some simple aeration, simple operation. I didn't want to do something that was going to require frequent, careful calibration. Like I said, my staff was not tech savvy. I've got some new guys that like technology a whole lot more, but they may be gone, and then I'll be, you don't know who you're going to have. You don't know how long you're going to be at a facility, and you don't want something so complicated the next guy can't run it, because again, it's not your money, it's the public's money. You want to give them the best long-term solution that's going to operate without with minimal human interaction. So we set up a control scheme that compared the incoming flows to a preset stage level and activates additional aeration as needed. We set on having a minimum of 4 units always running in our lagoon, and they operate. There's always 2 in a line in operation, but it's on an alternating schedule. So we're trying to not build up any big sludge piles because something was off for a long time because our flows were low. To kind of keep a baseline of oxygen and mixing in the lagoon. But the stage levels are adjustable based on, as we look at what our incoming BOD and solids levels are. If we want to make adjustments saying, I think we can scale this back, we've been really good on our permit, we want to change some things, we have that flexibility to make adjustments. And then on each aerator control panel, we had to add a communication radio. We added some current detectors and a few relays for turning things on and off, keeping everything in that auto. The handoff auto switch is always in auto. If you're going to shut it off, you shut it off at the master control panel, and that way, someone can see that, when they're not at the plant, and why'd we shut something off? What's going on? But overall, we did a nominal amount of equipment. There's very little additional maintenance. You're going to have a contactor go bad or something else, but that's going to happen regardless. And it's not a big deal to change that. Another thing that I always push for is, if you do an energy project, you need to come back after the fact, a year after operation, do an audit of where you're at. Did you achieve the energy savings that you thought you were going to achieve? If not, what happened? If so, what else can you do to end up better? We ended up reducing our energy costs over the first year by 20% per gallon of wastewater treated, and we've made some adjustments to our programming with our integrator to try and tighten that up some more, because I think there's additional savings that we're not realizing. The other part that does is we've kind of monetized the cost of our inflow and infiltration. So when I'm talking to my board saying, look, we need to invest more on solving these issues because we're wasting money elsewhere, whether that's at the lift station or at the sewer plant. And if we're cutting our flows down here, we're saving money further down the line. You're not just saving the energy up front, but if you're running equipment less, you're going to stretch out that life cycle. You're going to add additional, life. If it's got a 12-year life, if you're running it continuously, maybe you can get 20 years out of it by dialing that back some. Don't be afraid to look at what you can do to further your system and stretch every penny out of it to get where you want to be. So that was really all I had, is just, here's where we've been, here's what we've done. And thank you, Cassie, for asking me to give a brief overview of that.
Thank you so much, David. I think what you discussed really, really complements what Ben was saying too, in terms of making sure that you have the staff and the capacity. And I really love your plant's example of how you mitigated that and still have controls, but something that, can be picked up and used if you leave or if somebody else at the plant leaves. That's so important. So thank you for highlighting that. And I think it really complements what's been discussed today.
Yeah, and for our facility, Cassie, we added an internet connection so that our integrator has access. So if we want to make a change, it's a phone call and it's 5 minutes for them. There's no site visit. Half the time there's no bill because it takes them longer to generate the bill than it does to say, oh, you wanted that? Okay, it's done. How do you like that? So if you have that ability, if you're going to have internet at your facilities anyway, spend the extra couple $1,000s, get a good industrial firewall in there, but make sure the right people have access and make everybody's life easier. I mean, if I have a problem, I can see it on my couch at home. I'm not going to work at 2 a.m. I'm going to flip over my laptop, click a few buttons, and go back to sleep.
Definitely. Makes it easy. And I love your comment too on the slide about adding controls and getting those incentives from Ameren, Illinois. I know ComEd also has those incentives in their territory. And if you're part of a municipal aggregation, you can get some custom incentives potentially too. So there's definitely funding available. So thanks for highlighting that, because one of our questions was, how does the cost of installing and maintaining DO monitors compare to a manual control process? And I think you covered that, David, but David or Ben, do you have anything to add to that question?
I would just add that when you're looking at adding DO monitoring, it's important to understand the full cost of it. So not just what it costs to buy it, but what it costs to maintain it. And to David's point about understanding your staff, do you have someone that can calibrate it? Is that going to be above their level of expertise? And, understand the full impact of it. Once you've got that, though, if it makes sense, if you look at the dollars and cents and you see payback, you're talking thousands, not tens of thousands for most systems to automate DO control. The adjustments to your ladder logic and your PLC, I can't really talk to what that would cost, but I think we all need a referral to David's integrator, because if he's getting things made, if he's getting those changes made and not seeing a bill, I need that man's name for sure.
It's not all the time. Don't take it like that. But yeah, he's very he's willing to work on things to get where you want to be, not where someone else thinks you should be.
That's great.
And really and truly, I think David will agree with me on this. The biggest benefit to automation is that it's keeping an eye on your system when you're not looking at it.
Absolutely.
And we're on a session here to talk about lagoons. So we're talking about smaller plants, smaller municipalities, smaller staffs. And the time that you're not looking at it represents the majority of the time for most of these communities. So having a system that can run passively, and David, I love that idea you have for staging surface aerators on and off in response to flow. What a neat idea that one is. But yeah, understand your staff, understand your system, understand your operation, and look for areas to improve.
Awesome. Well, thank you for both of your comments on that. And if you have a question for one of our speakers, we have a little bit more time, but just wanted to note there's a couple good comments in the Q&A box about, typical mistake with facultative lagoons retrofits is placing alternative aeration devices without removing the sludge. No matter how efficient aeration device is, it'll never overcome the oxygen uptake by the anaerobic sludge. Do you have anything to add to that comment?
David, do you want to weigh in on that? I've got some thoughts as well.
I could say, yeah, there's the lagoon that I inherited. It was submerged aeration, and because of the amount of sludge, they slapped surface aerators on there, and so we're 20 years past that point, still dealing with the sludge, and now I've got old aeration tubes that are floating to the surface, so it looks like I have the Loch Ness monster in my lagoon. But yeah, trying to take a cheap solution and just ignoring other problems you have is never a good solution long term. It may look good on paper up front, but it'll cause you problems on the back end for sure.
Yeah. I will just add that at Triple Point, we follow a gentleman by the name of Steve Harris, H&S Environmental. He's a primary consultant that the US EPA uses. And you may have actually seen him talking about sludge in wastewater lagoons. He had a webinar last month that the US EPA put on. And when you talk to Steve and you ask him the question, he likes 18 inches as a threshold. He says below 18 inches, probably not going to interfere too terribly much in the operation. Above 18 inches, you start to talk about feedback of nutrients and diminution of treatment volume and all of that. And I would caveat Steve's comments by saying that 18 inches is a relative number. 18 inches, if you've got a 3.5, 4 foot deep facultative pond, is very much more significant than 18 inches if you're running a 13-foot pond. But yeah, 18 inches is a number that we like pretty well as far as talking about sludge and when it starts to become a problem. Sludge removal is an interesting conversation also, and basically about three main approaches to it. It's either removed through dry removal. You take the pond down, you use other ponds for treatment, you let the sun dry it out, and then you get in there with earth moving equipment, and you scrape your pond clean. The dry tonnage all goes off, pretty easy to do. The next approach is wet removal or dredging. And that's a system that comes in a boat on your pond where they're attempting to suck the sludge up out of the water and evacuate it from the system. It gets dewatered outside of the system at that point. And then the third main approach is bioaugmentation. So there's a number of different companies out there that will sell you a bag of bugs, sludge reducing bacteria. It's important to understand, though, that you've got a volatile and a non-volatile component to your sludge. The organic matter will be consumed if you get enough SRBs in the pond and you've got enough mixing that you can get them in contact with the material. The inorganic component, the sand and the grit, it doesn't matter what you do, that will not leave your system until it is mechanically removed. I could talk for a whole lot longer about sludge. I just thought I'd share some thoughts.
Yeah, maybe we could have another program on that for sure. Well, thank you so much. We are at time. We're 15 minutes over, but thank you all for hanging on the line. We've got such good content. And thanks for those that recommended we start a little bit earlier. We'll do have an hour and a half webinars next time just to make sure that you all set that time aside. But thank you so much, Ben and David, for speaking. Your presentations were wonderful. I was really excited for this session, and I'm even more excited after hearing you both speak. So thank you so much for your time and sharing your expertise today. Just a reminder that CEUs, you don't have to email me about them. I will email you a certificate and the course number when they're ready. Again, we're recording this session, so please, I will get those slides and the recording to you here later today or tomorrow. And we will have a couple of events coming up in the spring, so stay tuned for more information. So thank you to all the operators who were here today. Thank you again to Ben and David for joining us, and I hope you all have a wonderful afternoon. Take care. Thank you.
Thanks, Cassie.
Bye-bye.
Thanks, everybody. Bye-bye.